So we'll start studying reduction to exact ODEs. Before this, in our last lecture, we studied exact ODEs, and we also studied that exact ODE has a solution like this. If an ODE, an ordinary differential equation, is of type ODE, it has a solution like this, that it is has a solution that we have a function u of xy and it is equal to some constant c. But in order for this equation to be an exact type of ODE, it should fulfill the necessary and sufficient condition, and that is this equation. So if this necessary and sufficient condition is fulfilled, this type of ODE, this ODE is an exact type of ODE, and it has the solution this u of xy is equal to c. So this is what we studied in last lecture, and we solved an example. But here in this lecture, we'll study that if we are given an ODE that looks to be exact, but it doesn't fulfill this property. Partial m or partial y isn't equal to partial n or partial x. What should we do then? Then we should introduce if. So one will be reduced to an exact type of ODE, that when we will be given an equation like this, m dx plus n dy is equal to 0, and we check partial m over partial y and partial n over partial x, and they don't come out to be equal to each other. They don't come out to be equal to each other. So what should we do then? What would we do? What would we do then? It's a question. What would we do then? If you are given an equation that looks like this, something multiplied by 3x plus some function multiplied by dy is equal to 0, and you check the necessary and sufficient condition, and it is not fulfilled, partial m or partial y doesn't come out to be equal to partial n or partial x, what should we do then? Right now, we should do something smart to make it exact. So we're going to study this reduction to exact ODE. In this lecture, what will we do then? We'll do some trick. What is the trick? What is the trick? Trick to do what? Trick to convert it to reduce it to reduce this equation to exact ODE. To an exact ODE. So we're going to apply a trick. Set exact ODE. What's that trick? What should be the trick? Let's do this trick. Let's multiply. Let's introduce a factor. Let's introduce a factor, and we call it f. Introduce f, and call it an integrating factor. Call it an integrating factor, right? So we introduce an f and we call it integrating factor. What we are gonna do with this f, we'll multiply this f with m, with this n, and with this 0. So actually we multiply this f on both sides of this equation. We multiply f on the left hand side and the right hand side. So 0 times f, it remains 0. So now we're going to solve this equation. And we'll choose f such that after we have multiplied this and this, they become then partial fm over partial y is equal to partial fn over partial x. Right. F is such that the necessary and sufficient condition is now fulfilled. F is such that now this condition is fulfilled. And that would be great if we somehow find an f that if we multiply on both sides of the equation, the given equation that is not of exact type, it is reduced to an exact type of equation. That would be great. That would be great. Now the next question is how to find that f. But before we discuss on computing the value of f, let's see whether this technique or this trick works. Whether this technique works on a given ODE. So in order to convince ourselves that this technique or this trick of multiplying with f really works, we have to solve an example. So now we're going to solve an example where the given ODE, ordinary differential equation, isn't an exact ODE. It's not an exact ODE, but we'll reduce it to an exact type of ODE finally. How would we do that? How would we do that? How would we convert this to an ODE? Of course, by multiplying f, an integrating factor. So let's first check whether this given ODE is an exact type of ODE or not. So what we have to do is we have to apply the check, partial m over partial y. This is partial over partial y minus 1, this is minus 1, and the right hand side should be partial n over partial x. This is partial over partial x of x. It comes out to be 1. So since partial m over partial y isn't equal to partial n over partial x, this means it is not an exact type of ODE. So what should we do then? Of course, we can reduce it to an exact type of ODE by multiplying both sides by an integrating factor f. So what I'm going to do is I'm going to make a guess. I'm going to make a guess. So we'll not be making guess all the times, but we'll find a mathematical way to compute f finally. But for the sake of this problem only, let's make a guess. My guess is f is 1 over x squared. There can be, your guess can be different, and even with your guess you can fulfill this. You may find out that you fulfill this necessary and sufficient condition. So even all the guesses that we make here, they may not be unique. So my guess may not be unique, your guess would be different, your guess may be different, and your guess may also work. Right, so let's see whether my guess works or not. So I'm going to multiply both sides by f. So this is minus y times 1 over x squared dx plus x times 1 over x squared dy, right? So what I've done is I've multiplied both sides by f, and multiplying right side with 1 over x squared, it's the same, 0. So doesn't matter, it doesn't change the right hand side. Of course, it changes the left hand sides. So now the next is we'll reduce it to the simplest term, and then we may be able to apply the check again to see whether this is type of or not. And then we may be able to apply the check again to see whether this is type of or not. And then we may be able to apply the check again to see whether this is type of or not. So let's see what happens when we multiply this with this 1 over x squared, my integrating factor. This comes out to be minus y over x squared dx plus 1 over x dy is equal to 0. So next we can apply our check. Next we can apply our check, and that is partial m over partial y is minus y minus 1 over x squared partial over partial y. So this is minus 1 over x squared. So this is minus 1 over x squared, and partial over partial y is of 1. And the next is we'll apply this check. Partial n over partial x is partial n over partial x. This 1 over x can also be written as x to the minus 1. So partial over partial x to the minus 1. This is minus 1 times x to the minus 1 minus 1. So minus x to the minus 2, or minus 1 over x squared. So even this comes out to minus 1 over x squared. Oh, now we have done something really wonderful. The partial m over partial x or partial y is partial n over partial x, and they come out to be equal. Therefore this new ODE is exact. So by multiplying with an integrating factor 1 over x squared that we have chosen randomly, it comes out that the equation is of type exact. That now the equation is of type exact, and now we can find the solution. And we know that what the solution is, that if we have this, as the new equation, so the solution would be